Hi, we're going to take a look at digital logic data sheets today. We're going to start out with your classic 7400 series logic, in this case the 74HC00, which is a quad 2-input NAND gate. And we're going to go through the data sheet step by step, and we're going to take a look at what all this stuff here means, and we're going to go down into the specs and look at all of what this stuff means. Now we're going to take a look at the Texas Instruments data sheet here, and different data sheets will be slightly different in various ways. We might take a look at some others for the same gate, but your data sheets start out very typical. They've got the features here, the top level features. Now, one of the golden rules of reading data sheets is to not take the banner headline specs here at face value, because they could actually not just be wrong, but not wrong, but misleading. So they don't tell the full story. You really have to go down to the main specifications further on in the data sheet, look at all the little asterisks and the little numbers and everything else to really get a feel for it. But at a general level, it's not too mad. You know, it can tell you the typical operating voltage from 2 volts to 6 volts. For example, the typical propagation delay, which is TPD there. The output drive capability, but there's a trap in that one, which we'll take a look at potentially. And classic applications here in data sheets. These are, engineers typically get a little bit of a laugh out of these things. They're really there just for a marketing warm fuzzy. It's like, oh, I'm developing an enterprise tablet, so oh, look at that, it just so happens that this is the perfect part for that. It's like, no, like it's just ridiculous. I'm developing a PDA. Wow, it says that this is fantastic. No, we just get a little giggle out of those. Anyway, and often you'll find on the front page here, you'll find what packages they're available in. In this case, they're available in your regular PDIP, which is plastic dual inline package. That's the one you're used to, that plugs into your breadboard. And then it has the associated part number here with it. So you've got to have the N on the end. You'll notice that the numbers make a difference. And if you add the NS on the end here, then it's the SO package. So that's the surface mount package. So it's very different. So when you go to order these parts, just be careful that you do get exactly the right number from DigiKey or Mouser or whoever you're actually buying these from. Otherwise, you'll come a gutser and order the wrong package. So we're looking at the 74HC00, which contains 4 independent 2-input gates there. They perform the Boolean function, and we've gone through, NAND, we've gone through that in a previous video. Now we've got our table of contents, nothing fancy here. Look out for the revision history, by the way, of these, because often they might change some important stuff from revision E to F. What have they added? They've changed the ESD, they've added the ESD ratings table, had they? Yes, maybe the old data sheet didn't have that, for example. Added a military disclaimer and things like that. But there can often be really important changes, especially in complex modern devices like microcontrollers, for example, can have really important differences in the revision history. They can have all sorts of silicon bugs. And then we've got our typical pinouts here. These are for pretty much all of the packages. So for the SSOP, the SOIC surface mount ones, for the dip, plastic dip, the ceramic dip packages. Oh, by the way, we didn't show up the top here that the 54HC, this is the military version, the 5400 series, and that has a ceramic dip package version. It's just a more robust version, than your regular plastic dip package here, because the military like their ceramic dips. So anyway, let's not get mixed up in that. So you've got your typical pinouts. You've got your pin 1 identifier up here, and unless they say, well, yes, they do say here, top view and top view. So looking down from the top of the chip. Don't make the mistake of getting that back to front like you often do on these like surface mount leadless chip carriers. You might think, oh, these pins, because they're hidden on the bottom of the chip here like this, then I've got to flip the chip over in order to look at the pins and see which is pin 1. This is top view, so don't fall for that one. And there's the pin 1 identifier, which will typically be a silk screened or a laser marked circle on top of the package. But not all packages will have that. You've often got to go right down to the bottom of the datasheet, which we'll take a look at later, to get the physical identifiers. Then you can have a look at the pin functions here. The pin function table, as it's called, is often very handy. It gives you an overview of what the actual pin is. Like this is the gate 3 input, for example. By gate, we're not talking about a MOSFET gate, for example. We're talking about a logic gate. So we're talking about one of the NANDs. Remember, this contains 4 different NAND gates, and they're actually numbered. This first number down here like this. So 1, 2, 3, and 4. So input A. So this is gate number 1, input A, gate number 1, input B, and gate number 1, output Y. And then on your larger packages here, there's a bunch of NCs or not connected, and it tells you that there's no internal connection there. And of course, ground is your ground pin, and VCC is your positive power pin. If you didn't know what VCC means and, well, where that actual term comes from, we won't get into, but you look in your functional description table. It's the power pin. Thank you very much. Now, here comes probably one of the most important ones here, the absolute maximum ratings. Now, do not exceed these under almost any circumstances, okay, because you will basically ruin your device. It'll blow up, the magic smoke will escape, whatever, okay? So let's take a look at our supply voltage VCC here. A minimum of 0.5 because it's a reverse diode protected. Anyway, we won't go there. It's got a maximum of 7 volts, so do not exceed 7 volts. But you might remember from way back up the top here, it said wide operating voltage range of 2 to 6 volts, and that is the operating voltage range. This is the absolute maximum specs. Just because it's on there doesn't mean you can operate this chip at 7 volts. No, that's just where you won't do major damage. Okay, let's have a look at this input clamp current here, and it's plus minus 20 milliamps like this. Now, if you have a look at the conditions under which it's valid, the VI, which is input, is less than 0, or VI is greater than VCC. That means the input is less than the supply rail or greater than the supply rail. And that's important because inside the, let's have a look what's inside this data sheet. Actually doesn't have it, otherwise I'd show you the diagram. But basically this is the VCC pin. This is the input pin like this. Okay, so that's our input pin, and then that buggers off to our internal circuitry. They've got these internal clamp diodes here, and that's what they're talking about, the clamping current. So when this input here goes, say, plus 6 volts or whatever, that's bigger than VCC up here, which might be 5 volts. So therefore, current is going to conduct through the diode here, and that's what they're saying. You want an absolute maximum there of plus minus 20 milliamps. So anything over 20 milliamps and you risk actually blowing your input clamp diodes. So don't exceed that. So how do you avoid exceeding that? Well, I've erased my little diagram here, but if you know it's going to clamp, you have an input current limiting resistor like that. So depends on the maximum voltage V max here that you have on the input, you choose that resistor value to limit the absolute current through that clamping diode to plus minus 20 milliamps. If you're looking to protect your device from overloads via this clamping mechanism, which you might if it's hooked up to any sort of like external circuit, for example. Next up, we've got continuous output current here, or I/O. O stands for output, of course. It's plus minus 25 milliamps. So if you've got your NAND gate like this and you're powering this from, say, a 2.5 volt rail to make it nice, then you basically don't want your load to exceed 100 ohms. If you do, then that's going to exceed the maximum value here of plus minus 25 milliamps, the continuous output current. So the instantaneous could be higher, but they're not going to tell you that. It's the continuous output current. So anything lower than 100 ohms, you've exceeded your absolute maximum ratings, and the magic smoke could escape. Don't do that. So you might think, aha, plus minus 25 milliamps, that sounds pretty grunty. I've got 4 of these gates, therefore I can have a maximum of 4 times 25 or 100 milliamps coming out of this chip. What? No, you can't. Look at the continuous current through VCC or ground is only plus minus 50 milliamps here. So you can only take a maximum of plus minus 50 milliamps continuous from the actual chip. So if you've got your chip like this, and there's your 5-volt rail or whatever it is, and you've got your 4 outputs here, the total current on all these 4 outputs is not to exceed 50 milliamps. Even though you've got that wonderful plus minus 25 milliamps there, for each output, the total is not to exceed 50. Otherwise, you'll just blow up something internal. They'll also tell you what ESD rating this chip is for, because these most modern chips have ESD protection on the inputs, and they can survive the human body model. We won't go into details, but basically plus minus 2000 volts can clamp the input, no problems whatsoever. It can survive that electrostatic discharge, but as always, if you're really looking to protect your devices from external static shock, then you might have an external static clamp that can dissipate more energy than this particular chip can. But still, it does have ESD protection built in. Now up here we saw our absolute maximum ratings. As I said, you are not to use these as a design specification. You are not to design for those. They're just absolute, you're going to break the damn thing. If you go down here, here it is. Recommended operating conditions. This is the one you want to design around. So you saw before how we had a maximum supply rail of 7 volts there. Do not operate at 7 volts. It's actually 6 volts is the safe recommended operating condition for this chip. So don't exceed 6 volts. Now, of course, we'll have a minimum operating voltage here of 2 volts, and of course, you can go under that if you want, and you're almost certainly not going to damage your chip, but it's not guaranteed to work. The logic in there is just not going to function properly unless you've got that 2 volts minimum. Now, a very important parameter is VIH and VIL. You'll see this for all sorts of digital logic. It's universal across the board. And V stands for voltage, of course, and then IH is not IH, it's I and then H. So I means input, just like O will mean output, and H means high, and L means low in the digital logic scheme. So VIH here is voltage input high. So the high level input voltage, it tells you there. Fantastic. Now, this is actually split into 3 different specifications here for 3 different values of your supply voltage, for example. So the value is actually going to change with the supply voltage. It's a ratio metric, as it's called. So unfortunately, if you operated at the normal 5 volts, well, it sits somewhere in there slightly above that, so they actually don't give you it for the nominal 5 volt figure. So you've got to go, it's somewhere between 3.15 volts and 4.2 volts. Now what VIH actually is, let's have a look at this. We've got our NAND gate here, okay? Let's have a look. We've got our 2 inputs here. So we've got our threshold, we've got our 5 volt power supply up here, and our 0 volt ground, okay? So we're looking at the input pin here. So what VIH is going to be a level up here somewhere. So let's say we're working VCC 4.5 volts up here, okay? 3.15 volts minimum. So if we have a look down here, this is actually going to be 3.15 volts. And then our low level threshold VIL here, once again, at 4.5 volts is going to be 1.35 volts maximum. So it's going to be 1.35 volts. So this is the threshold level of our digital logic. So if our input signal goes up like this, let's say it shoots up like that and comes back down, oops, it never got to a point where it actually reached this threshold here. So let's say we had an input which goes, wow, just like that for a split second, then our input here is actually going to register as a logic high. And likewise, if our signal just went down like that, as long as it goes through that threshold level there, it is recognized as a logic low. But if the signal is inside this deadband here, then, well, it's undefined, basically, and you don't know what the digital logic gate's going to do. It can't be guaranteed at all. But you have to actually be careful with these because, look, these are max and minimum values. So this is what they guarantee, but you'll notice that they don't give a nominal figure in here for these. So, you just have to design around the min and the max. Sometimes they'll give a nominal, sometimes they won't, depending on the specification. But these figures are what they absolutely guarantee at that voltage. And over the operating free air temperature range. So that's over the full operating temperature range of this thing, which is down here. For the regular 74HC non-military stuff, it's -40 to +85 degrees Celsius, or your typical commercial temperature operating range. Your military ones, your 7400 series, just basically they're the same, but they're rated for a much higher temperature range. Now let's have a look at the DT/DV, or delta T versus delta V, and that sounds complicated, but look at the label here. It's the input transition rise and fall time. So basically, if we're looking at our input signal, it's how fast our input signal ramps up like this. So let's actually have a squiz here. Okay, let's say this is our input, and it ramps up like that. Okay, so you're going to have a time there between there, and that might be, say, 1 millisecond to get from 0 up to VCC, or it's actually, in this particular case, it's the transition time between these threshold voltages here, essentially, because that's what we really care about. We care about how much time the signal is actually spending inside this dead zone here. Now, in this case of 1 millisecond here, we're going to fail. Look at the specs here. There are 1,000 nanoseconds at 2 volts, or at, say, at 5 volts there, it's going to be, just call it 500 nanoseconds. For example, that is the maximum, because we're talking about maximum here, transition time. So it has to be faster than that. It's got to ramp up at least in that 500 nanoseconds for a 5 volt rail, for example. If it doesn't, then the gate is not guaranteed to work. It could go metastable. It could do anything. I talked about metastability in a previous video. It's just not guaranteed to work at all. So you don't want slow rising inputs. That's what Schmidt trigger gates are good for. These are not Schmidt trigger gates. So you need to have fast transition, rise and fall times on your input for this particular type of CMOS logic, or pretty much any CMOS logic will have a maximum transition rise and fall time unless it's a specific Schmidt trigger type. Next up, pretty much any device will have thermal information, or the thermal resistance of the package. Now, because these aren't power devices, they're just simple logic gates, they're not designed for power dissipation, but if they were, it's still all relevant. I won't go into the various details. I've done a comprehensive video on thermal information that I can link in at the end of this, but basically it's the junction to ambient thermal resistance here which matters. Or let's say you wanted to put a heatsink on top of this one, you'd be looking at junction, which is the semiconductor junction inside the thing, to the case, the top of the case where you want to put your heatsink onto. So if you had a plastic dip package, here's the value. It's 45 degrees C per watt. So if your chip was dissipating 1 watt of power, then it would increase there would be a temperature differential between the internal junction and the top of the case of 45 degrees. So let's just say the top of your chip happened to be measuring 45 degrees Celsius. Well, that's not what the temperature of your silicon die inside is at. It's at 45 degrees plus 45.1 or 90.1 degrees Celsius inside your chip due to that very high thermal resistance. But we won't go into details. That's more relevant for power packages. Okay, let's have a look at VOH here, or VO stands for voltage, O stands for output, H stands for high. So the voltage output high. Now, it's once again, it's got these at 3 different test conditions for 3 different output high currents when you're actually sourcing 4 milliamps, 5.2, or a very low 20 microamps as you would if you're just driving some other gates or something like that. And then for each one of these currents, you get 3 different specifications for the different voltage supply values. Now let's take this example here of VCC equals, well, VCC equals 6 volts here. Now you'll notice that typically, like minimum, it's going to output not 6 volts, it's going to output 5.5, for example, or nominally typical, say at this could change with temperature, for example. So the typical value could be 5.8. So once again, if you're gonna design, if you're serious about your design specifications and your margins, and you're building a probe that was going to Pluto, then you'd be designing around these minimum values here. You wouldn't be designing around the typical ones. You would go, well, this is going to be my worst case, so I'm going to design around that. But for general design use, where it doesn't, it's neither here nor there, then typical values are just fine. But what it shows is that our supply pin is 6 volts, but we're only getting 5.8 volts output. So let's actually draw our gate here. Okay, so we've got our NAND gate. Now, this is our 6 volt supply pin. Inside here, we have ourselves a little transistor like this, which is going to the output pin. And then if we have a resistor, which is then going down to ground, this here is not 0 ohms output, okay? It has a resistance, and you can calculate that output resistance based on the drop there. So we're getting a 0.2 volt drop at 5.2 milliamps output current. So use Ohm's law. Oh, that's homework for you. Use Ohm's law. Oh yes, there's the temperature I told you about at ambient temperature. I forgot to mention that. So anyway, you can essentially work out the output resistance of the effective output resistance in quote marks of the MOSFET inside there. It's not, I've drawn a JFET, but it's actually a MOSFET, and the output resistance of that at various currents. That's why the difference in this voltage here is going to get higher and higher the higher your output current gets, up to that maximum. You remember where it said 25 milliamps before was our maximum current, output current on the pin? Well, you can imagine how far the output voltage is going to drop based on 25 milliamps output current. If you're driving a LED, for example, at 20 milliamps or even 10 milliamps, it's going to have significant voltage drop, and that may not matter. But if you're driving something else where the output level is actually going to be an issue, then, well, you could kamikaze, and you've got to take all that into account. But normally, it's not a problem. But that's all part of reading the data sheet. This is what it all means. And VOL here is exactly the same thing, except we've got another transistor. Well, actually, I'll show you. We've got another transistor down in here like this, which goes down to ground, and that would be if we had a resistor going up to VCC like that, and then we've got current flowing through like that. Once again, you've got a certain dynamic resistance there of your output driver MOSFET, and that will be, once again, determined by these figures here. It won't be 0, it'll be 0.26 volts there, for example, at 25 degrees C. And you might notice that the 74HC, the military version, actually is worse than the commercial one. What's going on there? Well, you saw before the operating temperature range. The military 5.4 series logic is designed for a much wider temperature range, so the specification is actually going to be worse for that. It just comes with the territory. All right, let's look at I here. Once again, I is current, and the little I there is input. So the current on the input, i.e., effectively the input resistance. And once again, they give you a range over that's valid. They're basically saying just over the full operating voltage range there. Once again, at a typical ambient temperature. And once again, we have a typical value here. You'll see it's typical, and you can use that. But once again, if you were doing worst case design analysis, you'd go with the maximum, okay? And there's a hell of a difference. Look at how many orders of magnitude difference there, right? 3 orders of magnitude difference between your typical value and your maximum. So that's a hell of a lot of order. All right, so our typical value plus minus 0.1 nanoamps, that's 100 picoamps. So obviously this is a CMOS gate, right? There's hardly any input current whatsoever. You can, do simple Ohm's law to figure out what the effective input resistance is at that particular voltage. But it's basically bugger all. But once again, that's going to change with temperature. So if you're relying upon that for some super duper ultra whiz bang low power design, that could matter. Watch out for it, and you could come a gutser there, because these typical values, basically the typical values here are not, they might even say it here in the data sheet, I'll have to check, but the typical values are not actually parametrically tested at the factory. They're just typical ones. They might batch test them occasionally or something like that to make sure that they're still meeting those typical values. But the chip you buy, you can't go to them and say, I measured 1 nanoamp at 25 degrees C. They're going to come back to you and say, well, tough titties, it's plus minus 100 nanoamps. That's all we guarantee. Your problem, not ours. And now we have our ICC, which is basically our power consumption of the device. I think it had that at the top level spec, didn't it? Low input current, low power consumption. There it is. 20 microamps maximum. So let's have a look if that matches down here. I haven't checked this yet. 20 microamps, will it? ICC, 20 microamps for a 7.4HC. Yes, it does. There you go. There's the maximum figure at VCC 6 volts. So they've done the maximum voltage there. So it doesn't matter. You'll notice how they've got different input conditions here. It doesn't matter whether the inputs are at VCC or 0, and it's also at 0 output current, of course. You can't be drawing any output current, because then that will contribute to the chip power consumption on the ICC pin. So this is with the output pins floating. And of course, this is a maximum value here. So there you go, 20 microamps for those playing along at home for a 7.4HC00. That's, geez, fly halfway to the moon on 20 microamps. Geez. Anyway, let's continue. But that 20 microamps is actually over the full temperature range at the ambient temperature range of 25 degrees. You'll notice that it's only 2. So, it's an order of magnitude better than the banner spec right up the top. So if you just took that banner spec, yeah, that's worst case over the temperature range, but you're not going to be using your product at minus 40 degrees, for example, or right up at plus 85. So, and generally the chip, the die itself, is not going to be at an elevated temperature because you're not dissipating any power or anything like that. So, really, like 2 microamps is, if you're designing a low power widget, you might say 5 or something like that, perhaps. Of course, you can characterize it yourself, but they don't provide any further characteristic graphs on these things, and they don't provide any typical figure as well. They only give you a maximum figure. Now, C is for capacitance, and I is for the input, of course, and from any over the full operational voltage range, and because it's capacitance, the units are picofarads, or puff, if you want to sound like an industry veteran, then typical value of about 3 puff on the input. So if you've got your gate, I'll just draw an inverter, but if you're driving several gates like this, So, there could be reasons why you're doing this. Then, system design, just basic system design means you often drive in more than one gate. Then your total load, CL, load on the output here, is actually, 3 of those typical capacitance. And that could matter for your slew rate up here. Where was it? Here you go. That could be a big deal for your input transition rise and fall times because you're driving a capacitive load. So just be aware of that. That can be a big deal. And maximum fan out was a big deal back in the day when they designed computers with 74 series logic, because you'd have one chip driving 20, 30, other chips. And it was a big deal. And capacitance of the input pins really mattered. But that's not the end of the story there with the capacitance. In fact, it's just the start of the story. That CI is effectively the static capacitance. But what we've got here is a much more complex thing called CPD. And I could probably do a separate video on this. And this is the dynamic power dissipation. They don't say it's dynamic here, but it is the dynamic power dissipation capacitance per gate. And even though they're talking in terms of power capacitance and power dissipation, the units are still in picofarads, puff. So it's much higher. It's actually 20 picofarads. Once again, that's a typical figure. They don't actually specify a maximum figure for that, but that's for a switching device. So in a complex system, this one here, important one, and not just the static value here for an individual input. So anyway, I won't go into details there. We don't have the time to do that here. But yeah, there are 2 different figures there for capacitance. One CI and one CPD, dynamic power dissipation. Now let's look at TPD, or T is time, so our units are going to be seconds, nanoseconds in this particular case, and P is stands for propagation, D is for delay. So this is the propagation delay time. They give you exactly what it's for, from A or B input to the Y output. So let's assume that your input just goes high like that. There is no rise time. Let's just say it's infinitely fast like that. And then your output will, the TPD is how long your output takes to change like that. So your time in there is your TPD, or how long it takes the internal logic to propagate from the input through to the output. And there's a typical figure here. You might work from that, but once again, if you're doing worst case system design, maximum's where it's at. So, you don't want to come a gutser because you design around these figures, and then your computer works fine at 25 degrees Celsius, but when you stick it in a box and it's working at 40 degrees, or in the middle of winter it's working at 0 degrees, then you can completely come a gutser, and your digital logic system just starts having a fit. Weird errors start happening and you're not sure why. It's because you aren't taking into account the propagation delay. So let's say this is your input here, but this also buggers off to another input over here. Let's say you have another gate over here. It's connected, and then the output of this one here is also connected down to here. The output here is only going to be valid after this propagation delay time here, like this, because during that time, the output here is undetermined, for example. So you just got to make sure you don't come a gutser there in terms of your digital logic system design. And this can apply equally well to FPGAs, for example, PLDs, complex system design. It doesn't have to be discrete. Chips like this, you're going to get the same parameters like these for in internal gates inside FPGAs and other devices like that. Next, we'll look at TT here, which is the transition time. It doesn't tell you that in this particular data sheet. This one's a bit cryptic here. Other ones might be better, might be more descriptive in that aspect. So what it is how long it takes for your output to transition from low to high like that. And that's your time in nanoseconds. Once again, typical and maximum figures. So this TI data sheet actually doesn't give a huge amount of detail here because this could also be affected by the output capacitance. Doesn't say anything. Let's actually go over to a Nexperia datasheet, shall we? This is the, once again, it's for the exact same chip. It's for the 74HC00. And if we go down here, let's have a look at the exact same parameter. There it is. Yeah, this one actually tells you its transition time. Take a look at that. And this one actually has C figure 6. And look, this one gets quite intricate. Look at this, TPHL there. What on earth is that? Well, T, time, P, propagation, H, high, L, low. So it's the propagation delay time when it transitions from high to low output. So that's a combinatorial parameter that includes the transition propagation delay time plus the output transition delay time. See, we didn't get that nice little informative waveform, and you can go into more details on that. Oh, measurement points given in Table 9. Let's have a look at Table 9. Thank you very much. Look, it's all happening here. Table 9, input, once again. Aha, see, this one specifies a load capacitance. So when you your test circuit, you'll notice that it actually has a load capacitance on there when they actually measure these parameters, which they put in the data sheet up here. And check this out. Look at this. Wow. CPD is used to determine the dynamic power dissipation. There you go. This one has much more detail. I don't think we got that in the TI data sheet. And, you know, there's the formula is actually quite complex where all these things are taken into account to give you your dynamic power dissipation capacitance. And, you know, make a big difference. Oh, I just made an absolute fool out of myself, didn't I? Here we go. Parameter measurement information. They've got it here. Sorry, TI. Shouldn't have doubted you. I still got my TI TTL data book, which is like 4 inches thick. Anyway. So, yeah, there you go. There's the... I think we've gone through all of the specs, have we? Yes, we have, in the data sheet. Fantastic. Still more to go, though. So we've got all that fancy-pantsy stuff here, once again with a test capacitance of 50 puff there. Note A, CL, and that includes the probe and fixture capacitance as well. Trap for young players if you're not taking your probe capacitance into account, because they're going to be viewing waveforms on the scope and stuff like that. So you've got to take into you need a low capacitive probe to be doing that, or at least have it characterized and measured. Anyway, we're getting way out of the bounds of what we need to talk about for the data sheet. So we're done with all the specs, and there's a functional block diagram, whoop-de-doo. They're still updating this data sheet in 2016, which is pretty amazing. TTL's like 50 years old now. 74HC is not quite that old, but it's really getting up there. And there's our functional truth table, which we've done a previous video on. That will match your truth table. You should know your truth table for your AND gate, or you should be able to derive it. And a typical application. There's an SR flip-flop. That's just a... How do I know it's a flip-flop? It's just the cross configuration like that, and set and reset, and your Q and not Q outputs. So that would be equivalent to an SR, to a 7400 series SR flip-flop. You can build it with 2 NAND gates if you really want to. And we've just got some nice little warnings here. Thank you very much, TI. Take care to avoid bus contention because it drives currents that would exceed maximum limits. The high drive also creates fast edges into light loads. Routing and load conditions must be considered to prevent ringing. And that's all to do with PCB layout, routing, and stuff like that. And here you go, they actually explicitly tell you what we talked about before. Load currents must not exceed 25 milliamps per output and 50 milliamps total for the part. And outputs must not be pulled above VCC. Thank you very much. Just don't hurt your little gate. And we do have a parametric curve here. You don't often get parametric curves in just digital data sheets, but they've decided to do the transition time versus voltage here. So you'll notice that the higher up voltage you go, once you reach 5 volts here, it's pretty much a fixed 5 nanoseconds transition time there. So it's just faster. The lower voltage, if you're walking down at 2 volts off a single coin cell, for example, CR2032 coin cell, then you're working in this region. You're working in this region here, where you have much faster transition times. But not that it's going to matter, because if you're working off coin cell, well, you're going to be ultra low frequency anyway, like working off a watch crystal. So forget I said it. Then they're going to give you some handy recommendations on bypassing. In case you didn't know, I've done a whole tutorial on bypassing, so run into the limit of what I can link in at the end of the video, really. So they recommend your typical 0.1 mic, 100N, and recommend multiple ones for each power pin, commonly used in parallel, etc., etc. And then we've got some nice layout guidelines and unused inputs. Thank you very much. Tie unused inputs to VCC or ground like this. And they actually told you this up here, which I maybe forgot to mention, because if you're talking about, power package, power dissipation and stuff like that, that's going to be dependent upon, we recommend, I'll find it, don't you worry. Haha! All unused inputs of the device must be held at VCC or ground to ensure proper device operation. If you leave one gate floating, like the inputs to one gate floating, it's not really going to affect the other gates. It could on a more complex chip, for example. That's why they tell you. But also the fact that these are CMOS devices, if you leave your input pin just flapping around in the breeze open like that, then you're going to potentially get interference on that pin, and it's going to start switching, and then you're going to get, where is it? Your dynamic capacitance power dissipation. See? Whoop, come on. CPD. You're going to be dissipating power, pissing away power, because you're getting coupling on switching, especially that could be due to routing right next to it. It could easily couple a signal into that floating input pin, which could cause the input to oscillate, and oscillation equals more power dissipation. So do not leave your inputs floating. Tie them. Got it? Look at this, they even have a document implications of slow or floating CMOS inputs. And one of those, I don't even have to read the document, I can tell you, will be that excess power dissipation. So, yeah, just don't do it. Anyway, related links. Now we're getting into the community resources, blah, blah, blah. Technical, they link directly to their sample page. I wonder if you can get a sample for a 74HC00 these days. Probably. Anyway, now we get into the package option addendum, and this is where you actually get the orderable part number over here. So that was for the ceramic dip package. So if you're looking for your plastic dip package, where is it? Your P-dip over here, that's the one you want. Now let's actually have a look. There's actually two plastic dip packages here. One's got N there, and one's got NE4. Let's have a look at the difference. Both are lead-free. Lead ball finish. Aha! One of them has a different finish on the pins. There you go. So if that mattered, like a different metal finish on the pins. So if that mattered to you for really ROS compliance, but they're both ROS compliant, so they're both lead free. But if that mattered to you from a soldering perspective or anything like that, critical, if you're designing a probe, flying to Pluto, you've got one shot at this, you're going to have a dedicated engineer in the group just looking at the soldering and the metallurgy and all that sort of stuff involved in this sort of thing. So, so if your purchasing department ordered one instead of the other, that could ruin your space probe. And it looks like we've got more corporate waffle about lifetime buys and things like that if we make it obsolete, blah, 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 blah. Nothing else happening. Now we get it off. You package aficionados, here we go. Here's the tape and reel information. This matters when you're getting your device manufactured. Your assembly house really want to know this. They want to know, well, it's okay. It's a standard SO type package. They're probably not going to, they're just going to be able to handle it. But this, this can be important for specialized devices, and you can have them pin 1. It tells you exactly where the pin 1 orientation is inside the quadrant of the pocket like this, and it's important information. Your assembler needs to know this sort of stuff. So, manufacturers might be different. One manufacturer might have pin 1 orientation on the tape completely different to another manufacturer. Don't take it for granted. And in this particular case, they're all in quadrant 1 here of your tape like that. But, as I said, different manufacturers could be different, and how it comes in the box, for you box aficionados, there you go, How much shelf space it takes up. That could be important for a huge manufacturer. If you're Apple and you've got all these tapes and reels of components and stuff like that, all this stuff takes up shelf space when you've ordered, 20 million of these parts. Anyway, let's get on down here. And now we have our physical package requirements. These are the min-max. These are if all your mechanical engineers are all getting a bit moist now about the package. And there's the leadless chip carrier. So how that's designed if you were doing designing a pad, that just went, for example, your pad went around there like that, then this sort of drawing matters, right? So let's go down here. There's our SO package. Once again, if you're designing a pad that sits on your chip like that, it's a standard SO package, but hey, let's just assume that it's something weird you don't have the footprint for, you're designing your footprint, then, by all means, you've got to design your own footprint for this. And some packages like Altium, for example, other packages might have it, PCB layout packages, might have a IPC footprint wizard, for example, and you need all of the information contained in here. It'll have like a common format and stuff like that. It'll ask you for all these particular widths here. It'll ask you for your package width and stuff like that. So if you've got an SO package wizard generator that generates a footprint automatically, you just need to know this information, and you can get that from the data sheet. Oh, look at that. Wow, ceramic dual flat pack for those military aficionados. You could even cut out your board like this. You could even have like a cutout in your PCB like that, where your chip actually sits flat and is then soldered on top of the pads like that. Seen that in various teardowns over the years. Oh, look, we get actual photos. There's the ceramic dip. Nobody uses ceramic. Well, military still use ceramic dip. There it is. Yep. Yeah. No. And recommended footprints. Now, here's the thing. Some people are all for using the recommended footprints inside the data sheet for a particular chip. People will take that as gospel. Others will not. Nope. Never ever touch a footprint inside a data sheet. Never use it. You'll kamikaze. Your assembler will hate you. Use the recommended ones from your assembler, or you're an IPC standards aficionado. You only use footprints from the IPC. I won't get into the flame war of, all this. It's just not worth it. Anyway, there you go. So there's all your details for all your packages. Once there's your recommended SO footprint. Some people will not like it, others might, and your PCB package might actually have that particular thing up there for the small outline package. It may label it in that particular way, but yeah, important notice, probably don't use it in medical devices and stuff like that, and they're very serious about that, by the way. If you're designing your chip into a medical device and it kills someone, their army of lawyers will totally wash their hands of it. Does it even mention medical in there? I don't know. Anyway, important notice. Whatever. So there you go. I hope you enjoyed that. I know it's been a long video, but there's really no way to avoid that when you go through every single page of a data sheet and every single parameter. And this is for a simple 74HC 00 quad NAND gate. Imagine if we did it like a microcontroller data sheet or an FPGA data sheet or something like that. I could do, like, the video would literally be 24 hours long to do like an FPGA data sheet with all its parameters and everything else. But anyway, if you found that useful, please give it a big thumbs up. And as always, discuss down below if you like this sort of screen capture data sheet type thing. I can do more of them. Please leave a comment down below if you wanted me to go through other types of data sheets. This one follows on nicely from the digital logic tutorials I've been doing recently, but if you've got suggestions for other data sheets you want to go through, then by all means, we can do that. Hope you enjoyed it. Catch you next time.